Okay, good afternoon everybody. My name is Jussi Puranen from the Switch and I'm working as a product line director for the electric machines, and today I will give you a short presentation regarding permanent magnet machines for direct drive propulsion applications. So if we start from the basics, what is a permanent magnet machine? Well, it's a machine where the magnetic field is created by using permanent magnets instead of these conventional, let's say, electromagnets. For example, in this top picture, that is the conventional electrically excited synchronous machine where the magnetic field is created by feeding current into the rotor winding. And the drawback of that solution is that when you have a current flowing in the conductors, that will always create quite significant losses, and that's why the efficiency with these machines is always a bit low. But our approach has always been to make the magnetic field by using permanent magnets. So you can see one of these rotors on the bottom side, and these gray boxes on the surface of the rotor, they are the permanent magnets and they will create the magnetic field. And the benefit of this solution is that when you don't have any current flowing to make the magnetic field, you don't have any losses related to this. And that's why the efficiency with the permanent magnet machines is always better than with any other electric machine type. And of course in marine applications, this means fuel savings because all the energy must come from combustion engines regardless of the application. And besides high efficiency, other benefits of permanent magnet machines are that they are quite compact, meaning that there's more space for cargo, and also the inertia and rotating mass of the rotor, they are very small. As you can see, the rotor is basically empty space inside, so the inertia is very low usually with the permanent magnet machines. And this is the product lineup what we have regarding direct drive PM machines. So we have 3 different frame sizes. The smallest one is called PMM 1000, so it's permanent magnet machine, and then this number 1000, that is the shaft center height from the ground level in millimeters, and M stand for marine. And this PMM 1000, that is typically used, or that can go up to 3 to 5 megawatts with the nominal rating in propulsion applications, depending a little bit on the rotation speed. And then the next frame size is PMM 1500, and that can go up to even 10 to 8 megawatts regarding rated power. And the biggest machine size what we have, that is PMM 2000, and the height of this machine is about 5 meters and the same for the width, so it's quite big machine physically, and that can go even up to 12 to 15 megawatts from the rated power point of view, depending a little bit on the rotation speed. But then we have, in addition to these 3 different frame sizes, we have also different axial length variants, and this means that we can scale the axial length of the machine to be shorter or longer depending on how much torque is needed. So if we combine these 3 different frame sizes and all these axial length variants, we have all in all 50 different variants, and this means also that we can always basically perfectly match our machine into customer's application without any over dimensioning. And these are liquid cooled machines. So you can see this unit on the top, that is the cooling unit. So there are 2 heat exchangers, so there's liquid going in and then hot liquid coming out, and then these cooling fans, they will circulate the air inside the machine. And when the air heats up because of the losses, then the hot air will flow through these cooling cells, and then the air will go back to the machine, so it's a closed circulation for the cooling airflow. And we have different options what comes to electric propulsion, and this slide is for the single machine propulsion, or actually single propeller propulsion. So we can deliver the machine either with own bearings and shaft, or then without the bearings. So the picture on the bottom, this is the conventional solution where the machine has own bearings and own shaft, and then you just connect the shaft end with the coupling to the propeller line. So this is the traditional approach. But then we have also this, let's call it bearingless concept, on the top side picture. So this means that the machine uses there are common bearings on the propulsion line which support both the propulsion line and also the motor. And this makes the mechanical design simpler because there are less bearings on the propulsion line. So this kind of machine concept is also possible. But the basic machines itself, they are the same than what we have used in shaft generator applications, and currently we have around 150 machines running. All in all, we have sold about 350 pieces. So the only difference between shaft generators and these propulsion motors is that these machines include both the bearings and the shaft, of course depending a bit on the concept. And then we have also this so-called tandem concept, and this means that we have two identical machines connected into the common foundation. So there's a single shaft going through both machines, and there are bearings only on the end of the tandem unit. So in between the machines there are no bearings, and this makes the machine very short in axial direction. And what comes with, we can mount these terminal boxes on the machine end shield, and that will make the whole design very narrow because often the width is very limited in vessels. So that's why the terminal boxes are practical to mount into the end shields of the machine. And what makes this concept quite special is that each of these machines can be mechanically decoupled from the propulsion line in case of fault in the stator winding. So in that kind of event, the system can still continue operation with 50% of the full power. And this is very relevant from the classification society point of view. So this kind of concept can be used in vessels having only one propeller. And this is a typical efficiency curve. In this example, this is a 5 megawatt propulsion motor with 120 RPM nominal speed. So at the nominal point, the efficiency of the PM machine is about 96.5%, and as you can see, it stays very high throughout the whole operating range. Actually, it's even a little bit higher at partial load compared to the nominal point. And then finally about testing. So this picture is from our Lappeenranta factory in Finland. So at the moment we are able to make full load testings up to 18 megawatts, and basically all new machine types what we are doing, they are always type tested at full load, and we are using this back-to-back testing method. So it means that we have two identical machines and they are connected through the common shaft, and then one machine is operated as a motor with the frequency converter, and then it's rotating the second machine which is operating as a generator. And this way we can take full load out from the machines, and we can measure efficiencies, all the electrical parameters, vibrations, basically anything what is needed. And in this case example, the machines on the right hand side, they are 2.2 megawatt inline shaft generators, and then the machines on the left hand side, they are 10 megawatt PM wind generators. Yeah, that's all. Any comments or questions? If not, thank you.